Right. We can continue, guys. I hope you can all hear me. So given what we have just discussed now in this example, we now see comfortably that if you are right, hopefully you can hear me after logging back in. Can I get a yes in the chat, guys, if you can hear me and we proceed? Can you hear me? Okay, right. You can hear me. That's good. Okay. So since you can hear me, we can proceed. So from what we have just discussed, it implies that this is this one now here is the inverse. This is the inverse transform of our Fs. So if you just have this and you split it up like that, then you use our derived proofs for sine and cos. Then you can split it up like this and like this. Remember, this one here is simply b over s squared plus b squared. And this one here is s over s squared plus b squared. Then remember, it is ft. You comfortably come back to your ft, which is this one here. Right. Okay. You can clear this. Good enough. You guys are third years and you are all sharp in terms of, okay, so this is same story. Let me see what is in the chat. Okay, people are saying yes, they can hear me, I think, which is good. Everybody was telling me to repeat the example, which I have just finished repeating. That is fine. Okay, everything in the chat, I think, has been addressed. All right. Good. And someone is saying everything is obvious. Okay, so I can now increase the speed since someone has who can see what you share here, recording on. Okay, maybe this is some technological kind of feedback. Right. Okay. Yes, somewhere I'm with you. Somewhere says Turumbe. Good. Someone says, is it always to use the sign when finding Laplace inverse? This is who? Eno Konasasera. I've not really understood the question, but you use a function that is directly associated with the inverse of the given solution, whose function you wish to establish. Okay. So, Abiti said not everything is obvious. I thought you had said everything was obvious, Mr. Abiti. Okay, but now what I'm displaying here is obvious. Go, you find these things we have already done. Now, guys, trigonometrical. By the way, I've already encouraged you that I have a hard copy of these materials so that as we go through, you fill up the gaps, guys. Okay. Here, sincerely, if I go through this, I'll overly bore you. We have agreed with those people in the chat room that these are obvious things. So you just flip over the pages, the hyperbolic functions, flip. You just go and you do the integration. This is calculus 2 now. All right. Just flip. This is where I was supposed to start. If you recall, and if you are good students who are working for heaven or Janaz for Muslims, you will all concur with me that last time I said I will start here, unit step functions. So I've taken all the other time just going through some of the things we had discussed in the previous lecture, right? Now, unity step functions. These unity step functions are sometimes referred to as what we call Heaviside functions because of their stepwise nature. We have something called a Heaviside function. Heaviside function. These are kind of step functions. So when you talk of a unity step function, sometimes it may be called a Heaviside function. So because it is Heaviside in nature, then there are very many things that we can do. And why do we study these Heaviside functions? It's all about the applications associated with this. So if you have dynamics and you realize when you talk of step functions, this could be dynamics that goes like this. So what does this imply? We are saying, of course, here we say ut, which we are calling our step function, it is 1 for t greater than 0. The sketch here is not necessarily for this. I just wanted to demonstrate what we call a Heaviside function here. So it means that at this point here, when you are here, you can see here, this increases for a single value along x. Okay, so if this is your ut, the vertical. So, sorry, this is now not x, but rather t. This is t, not x. I told you my mistakes are your responsibility, guys. So this is a t here. So for a single value of t, you can see that this one is going up. And then you realize that for a single value, okay, this is for a certain multiple values of t, because if this is t naught here, then you can see there are changes in the values of t here along this direction here. But along with this, you have a single value of ut. So that's why when we see here, t is 1 for t greater or equal to 0, and it is 0 for t less than 0. This is to the left. So you have for a single, for multiple values of t. These are now multiple values of t. You only have a 1. So for example, if this is 1, then we are saying for t greater than 0. Of course, here t is greater than 0. We're in the positive domain. You realize that ut is fixed. Then after some time, you may have a single value where the u is going upwards. Then you have multiple values of t, but for a single outcome of u, which is that one there. So this is some kind of step function. And these step functions are key in the health sector. Some of you, if you have ever had relatives back then who suffered from HIV, some of those people would die due to drug intoxicants, the side effects of the drug. So what they would do is, any interval like this, you treat the person. So as you treat the person, you study the impact of the drug on this individual. Then what you do, because the side effects were so strong, or what we call the drug intoxicants, then what you do is you give that person what we call a drug holiday, or sometimes in the epidemiological language of treating patients, they are called the STIs, not sexually transmitted infections for you people who are obsessed with the fornication, but this is called the structured treatment interruptions. So when we say, how do you structure treatment? You structure treatment like cancer. If you've by bad luck had a relative suffering from cancer, those people are going to be subjected to what they call chemotherapy. This so-called chemotherapy is not a joke. They can subject you to it and all your hair goes. You've seen ladies who like hair, they beautize in their hair, but if you find a lady suffering from cancer, take it, leave it. If she's on a chemotherapy kind of treatment, you will find her with a bald head. Not that she has cut off the hair. The side effect of the drug takes off all of the hair. And if you never appreciated your wife or your girlfriend or whoever that lady is truly, then she may end up looking like a simigo. And you even say, I am no longer interested. But if you are married like me, however shape she takes you on, you are married forever. So to avoid those serious side effects, we bring in the STIs, which are called structured for S, treatment, and the I is for interruptions. You interrupt the treatment to give the patient a kind of breakthrough in recovering from the side effects. And when they try to do away with the side effects, you look at maybe how the cancer is growing. Those are called cancerous lesions. Then you say, okay, we can now subject you to another dose. Those are, we use these step functions or unity step functions or heaviside functions. So the applications are so heavy in the health sector. So if you're doing these and you come up this way, you do a master's and you're interested in those things, then we will subject you to a lot of those applications. And then your wallet will also be happy because there is a lot of money in the health sector. So STIs here, it's not sexually transmitted infections, but rather structured treatment interruptions. And these ones work a lot with what we have called this step function or the heaviside function. So that is just to motivate why we are labeling to go into all of this. But if you are out there and for you, your dream is to become a head teacher in a Kasidi school, perhaps you will never apply these ones. But me, I am explaining these things globally. You never know, you may become a head teacher there and somehow you change your mind and you say to hell with being a head teacher. Then you may come and you find yourself applying this. So it is a baby step format. We are initializing this, and that's why we are trying to comprehend here. Right. So step functions, we have understood why they are very necessary, and you can't do with these applications. And I've already said some members may have patients. So how do they work? And now we are going to use them here. Okay. Maybe I must comment. I've been giving you these short interval kind of links, but these short time links, they help in sharing the audios for these lectures. And why I've been giving you these short ones, they record in a short time and you can easily upload them, you can easily download them. Why? It's because our number has never reached 100. If the number reaches 100, this thing will not handle us. Then I'll have to use the other super platform of Zoom that can take on even 1,000 people. Problem with that is the recordings will be so heavy and bulky. You can end up with a recording of half a GB. And then compressing it compromises the resolution and the quality. So I see we are around 91, which is good. But as soon as our number exceeds 91, I'll have to send you another link that can handle or contain a group bigger than 100. Otherwise, once it hits 100, whoever will try to log in will not succeed. Okay, fine. So let's go through this now. When this thing warns me over the remaining 10 minutes, I'll go into the chat so that I don't lose the chats that you have sent. Okay. So from this, we now say, if you have, I've already demonstrated what this unity step function is all about, and we will revisit these step functions in Z transforms. So you have UT, which is defined as this, and now we have, we can have shifts. Remember, I told you if the function I drew, these functions are not used in statistically. I'm talking of a static motion. So there are shifts that are associated, and it depends on how the shifts flow within the phenomena you're trying to study or understand. So in this case, when we talk of a t minus a, this t minus a, this is some demonstration of shifts that we are going to look. We will even look at properties that govern these shifts. So you have ut minus a, this is some demonstration of a shift. And when we go to the few next pages, we'll discuss the shifts in detail. It could be to the left, it could be to the right. And the direction of that shift generally depends on, again, what you're trying to look at. So for now, I'm not going to overly dwell much onto the t minus a, given that we have a whole topic that we are going to deal with here. But for demonstration purposes now, given that we are introducing this, if we have ut, which is 1 for t greater than 0, and here it will always be 0 otherwise, all right? We are saying this would imply that if you have ut minus a, now here, because this is a t, of course, this is equivalent to having u t minus 0. Is that okay? So in this case, we are simply saying our a is 0. That's why we are saying it is greater than the 0 and less than the 0. Is that okay? Now, at this time, remember if this is the t scale, so here t0 we are here, now we have moved. Is that okay? So if you are at this spot labeled A, is that okay? So there is a shift from the origin to that. Now we operate with respect to that reference point, which we are calling A. So we are saying now for minus A, this is t greater or equal to A, but here it was 0 because we are centered at that. And here, same definition, but t less than the A. And here now we can even have now your u, but operating with respect to a certain given function. Remember now I can have ut minus a f of t minus a. So I have f of t minus a t minus a. Why? Because by definition this is 1. So I have 1 times f of t, which is simply f of t. Guys, you need to be alert here and sober. Otherwise, you will get lost. Hopefully, I'm with you. So I have my f of t. Remember, this was 1 t, t running from 0, rather from a to infinity, by definition of our Laplace, because we are going to use these step functions in the Laplace. So here you would be moving from a to infinity. Hopefully, we are together. So it is a step function. It will always be a, rather it will always be 1. But now if here we have f of t, so it is this f of t, but remember this gives you 1, which is simply f t minus a t running from a to infinity. And here it is 0 otherwise. Hopefully I'm clear there. So it means if I have, maybe for demonstration purposes, if I have L, the Laplace of 1, this is equivalent to me having a Laplace. This is 1 times u as a function of t. My worry is usually the crammers. So I'm demonstrating using this to avoid the people cramming these things. Can I hear a yes? If you guys can hear me, just a yes in the chat. Hello. Hopefully you can still hear me. Are you with me, guys? Okay, you are still with me. Now, if we have L, this is L of set T dot U T. If you want the Laplace of this, what would this mean? You have the ft. Now, what is the f of t minus a? That is the t. Then you have ut. But remember, by definition of ut, it is 1. This is from 0 to infinity and 0 otherwise. Or if it is t minus a, then it is a to infinity. That is again 1. So this one has a 1. So in this case, this one will remain, and I have a t into ut. Then it could be, maybe if I can now simply generalize it, if I'm to generalize it now, this is the same as f t, then u t. Now here I have generalized this thing. So what is the f? The f here was 1. That is 1, then ut, because it is this is the definition. You have a to infinity, and then this is 0. This is now from minus infinity to 0. This one is from minus infinity to 0. Then there it is a to infinity. So ft here now, if it is t, is that okay? In that case, now I'll be having my t here, f of t minus a. And that is what we are demonstrating here. You can see now this demonstration brings it out nice and clear. How? You now have L of u t minus a. But what is u t minus a? This u t minus a is 1. The whole of this is simply 1. That is this one here. We are substituting that one there. And it is from where? This is 0 to infinity. Yes, it is 0 to infinity. But according to this whole definition here, it will be f of t from a to infinity. That's now why we take this. But this is 1. So we have substituted the one there, that which is this one here. And if you do that, you get the final answer, which is this one. Okay. We can now proceed. So if we proceed, you end up with that answer. And now there are all of these others. So what is this? I have now, if you have not understood what I've demonstrated in the previous one, it is clearly demonstrated here. You see this? Just look at the answers. The answers are the same, which takes me back to what I've just explained. These answers are the same. This one is exactly the same as this. Why? I have told you, if you have L, this is f of t, you have u of t. Is that okay? But your u of t has been clearly demonstrated to be, this is 1 for t greater or equal to 0. And it is 0 otherwise, which is t less than 0. So if you have this one here, we go back here. Now you have ut, which is this ut here. I'm hoping those who are lost can now follow. The ut is this ut here. But what is f t in this thing here? The f here is a silent one here. There is a 1. So it means our ft in this case is 1. So if it is 1, what do you end up with? You end up with 1. So it means that if you have L of ut, this is simply the integral from 0 to infinity. Remember the definition of ut, it is 1. This is greater than 0, but the ft is 1. Remember, it is E minus ST f of t dt. But now the f here is 1, the silent one there. You just remain with this E minus ST dt. And when you integrate that, you have 1 over S. I hope we are together. Now here we have L of 1, but remember we discussed L of 1. If you look for t to the power 0, if you remember powers of t, you have L of t to the power 0. But we said that one gives us n factorial over the generic one. It is S over n plus 1. Guys, I hope you still remember this here. So if it is 1, that is t to the power 0. So this would be what? 0 factorial, which is 1, over n s to the n is 0, because here it is t to the power 0, which is this 1 here. So you remain with 1 over s, which is the same thing as this one here. I think I have exhausted that thing. Surely you have no questions on that. Okay. Yes, we engage gears. So I believe you have understood me there. And given that, now you can do this one here, you can do that one there. Just substitute directly into this here. If you substitute directly into this, you can see this one. We already demonstrated the other one there. Where was it? We demonstrated this one. So for these ones, you don't even have to waste time. Just look at, these things must be on your fingertips, guys. Once you have ut minus 8 is e to the minus, now the generic form, this is the generic form. This is what it will always give you. Now, once I have this on my fingertips, I can easily compute this, because now the a here is 3. Remember, it is minus a. So I just come into this and I substitute that my a is 3. So ut minus 3, this is 3s. And if it is, this is ut plus 2. Is that okay? So if it is ut plus 2, what is a? Remember, by definition, this was minus a, which gave this. So here it becomes e to the 2s over s. So you substitute, because now here you are looking at the a. I think we have to be a little bit careful here with the way we are playing with this. So the generic is t minus a. So if it is t minus a, you just have to look at this. This a is the a you have there. So generically, that is a minus. And you end up with that there. Right. Okay, we can proceed. If you proceed now, okay, there is a theorem here. Maybe before the theorem, I can look at the chat before we forget. Let me see what people are saying in the chat. All seems okay. Let me just flip quickly through the chat. Repeat the whole example. That one I had already worked on that. Most of these, I think, do okay. That was a bit it. Is always that one I answered. Okay, this is. I request that we follow the timetable. Now I'm getting confused. Okay, guys, we will do this, and we will do this, and we are remaining with the 10 minutes. There is someone talking of following the timetable. I thought we said we'll be starting at 9 and we end at 11. So I'm sure we are following the timetable. This is according to who. Someone talked about the timetable here. This is called who. This is Mr. Antambi, Frank Isaac Antambi. You request that we follow the timetable. The lecture is colliding with microwaves. I don't know. I've never heard of a course called microwaves. But anyway, I think the lecture is still on schedule. We agreed that it is 9 to 11. This lecture is correct. Okay, microwaves for physics. This is, I don't know why you keep saying it is colliding. Okay. These we have many collisions. Okay, these ones we will sort them out with we will sort these ones out with the coordinators. Okay. So I see physics students are dying with collisions. Then we have physics lecture going on now. Someone is asking, send the recorded sessions. Okay. I think most of what we have done is we have now someone here, this guy, in Tambi, I think you people are confusing things. You are saying your lecture starts at 8 and it ends at 10. No, I don't think. Okay, I think we need to resolve this, but I think this could be a mistake because I just have to we should avoid this collision so that people don't miss their other lectures. But as far as I'm aware, we don't have a collision. Maybe the coordinators can suggest another time slot on this day. But otherwise, I'm not very familiar with the collisions you guys are talking about. Okay, we also have another lecture from 8 to 10, so that won't work. Now I'm even more confused. This is Jocelyn. Okay, I think the issues of the timetable, these ones, you will sort them out with the coordinators. Okay. So for me, I'm supposed to finish at 11 and I'll finish at 11. But now you are saying the lecture ends at 10, meaning the lecture ended. Okay. So now we have here a very simple definition that we are going to go through and then we demonstrate. I think this one, we can use this to conclude the lecture today. And unless if you guys are free from 11. But let's just go through this. So we have a very simple theorem here. This is quite similar with what we have done. And I'm going to just summarize it for you. We've been looking at all of this. And here we are saying that, if you have, where is my color? Yes, here. If you have something like this, so we've looked at ut minus a, then the question is, what is the equivalence of this? This is very simple. This is a simple theorem that you can be asked to prove. And I want to finish it in the remaining 15 minutes. So to prove this, how do we go about it? We have already looked at the techniques. Since we already know the definition that GT is T, we have just looked at this. We have been discussing this one here. So we have GT, which we have, this is from A to infinity and 0 otherwise. Then we can redefine it like that. So if you have this, then the question, of course, this would be 0 otherwise, then you move from A to infinity. But remember, we have already discussed this. If you have A going to infinity, but remember the definition moves from 0 to infinity. Since it moves from 0 to infinity, guys, I want to finish this by 11. So if this thing runs out, just log in and we finish off at 11 exactly. We are finishing at 11. If this thing times out, because it is showing me something like 2 minutes remaining, just log back in. We finish off this theorem and its example at exactly 11. Okay, so what I was saying is we have already looked at this. Since the definition moves from 0 to infinity, then we can just redefine these inter limits here. And here you only need a certain x, which is, okay, it is even written here, it is here. X is t minus a. Why t minus a? Because if this t runs from a to infinity, I definitely know that when I'm changing limits, if t is now a, then x will run from 0 to infinity. This proof is very obvious because we have already discussed this. And if it runs from there, then I have to redefine my t here, because now t will be x plus a. Sincerely, I'm not going to waste time on this. This is what we have been discussing. We discussed it even last week. For those who have been with me and following, you know what is happening here. So let me just demonstrate this now here. So what we have is from this, we can comfortably come up with this one here. I'm sure no one can get lost here. Why? It's because we have already said that we have this that has been changed. And if it is changed, you have x. This one will come in because everything here is going to be redefined. So g, which is a to infinity, becomes 0 to infinity. We had a certain e to the minus s. But remember that t from here, it is now x plus a. So I have x plus a here. And when you expand this out, you'll get the e to the minus s x, which is this one here. But remember, this was gt. What is t? T, we have said t is x plus a. This is x plus a. So since t is x plus a, we replace that t, which is that term there. And you remain with the e to the minus sx, that is this one here. We take out the e minus sa, which is the term out there. Okay? From that, we deduce from this now, you can now, since it is a dx, you can take it back to t. And for you to take it back to t, clear this. For you to take it back to t, you just have to again change the limits, but that one is direct because you just now replace the x with the t, the x with the t, the x with the t. And once you do that replacement, you have this thing here. So what we discussed previously up there was for u t minus a. That is what we discussed, what we presented here. That is this situation here, that and that. Now here, we are looking at this scenario here. So in this case, we can look at one example. And this example, we are remaining with the 10 minutes. Those 10 minutes will be enough to demonstrate this. So what is this about? If we have you guys, this thing is timing out very soon. Log back in and we use the remaining 9 minutes.